It is a force. Okay, so Newton's first law says that an object at rest will remain at rest unless acted upon by an external unbalanced force. There are no external unbalanced forces acting on the desk. Gravity is pulling it down and the floor is pushing up. Okay? We don't always think about that reactive force of the floor, but it's there. It's why your feet get tired just from standing. Okay? Your gravity pulls you down into the floor, and the floor pushes back against your feet. That's what you can feel. Okay? If you're sitting for a long time, okay, you can feel it. Your butt gets kind of sore, okay, because you're just sitting there, and the seat has been pushing on your butt, okay, for however long you've been sitting there. Gravity's pulling you down, the seat's pushing back up, and that's why you don't fall down. Okay? There's always these forces that act in pairs. That's actually part of Newton's third law. Okay? But for right now, we're just looking at the fact that there are no unbalanced forces acting on the desk, and as a result, the desk remains at rest. The second part of Newton's first law goes like this. An object in motion will remain in motion at a constant velocity unless acted upon by an external unbalanced force. Okay? So what that means is, if I have an object that is moving at a constant velocity, in the absence of any other forces, it'll continue to do that. It'll just keep going. This is really important for astronauts. If they become separated from their spacecraft with no propulsion, they're screwed. Because they have no way to change their velocity, whether they're stationary or whether they're moving. Okay? They've got a problem. Because they have no way to exert a force that will change their velocity to get them back to their spacecraft. You guys follow me on that? Okay? In space, no one can hear you scream. And flailing does nothing. Okay? So you can scream till your oxygen runs out and flail your arms until you collapse of exhaustion, but it will do absolutely nothing because there's nothing to push against. I mean, really, flailing on Earth doesn't do anything either unless you're in the water. Okay? Then you have something to push against. But in the air, flailing your arms just makes you look silly. Okay? It doesn't really do much in terms of moving you around. It does a heck of a lot more than doing it in space does, okay? But it still doesn't do very much. Right? So if you ever become separated from your spacecraft as an astronaut, okay, always remember to bring something heavy with you. Because then you can use Newton's third law to get back to the spacecraft. Okay? What do you need to do with the heavy object? Right. Yes, and let it go. You can't just push off, you have to let it go. Okay, so like a big heavy wrench or something like that. Okay, if you have your back to the spacecraft that you want to get back to, and you throw something, when you push on it, what does it do? It pushes back on you, and it'll get you going. Not very fast, but remember, you're in space. Once you get moving, there's nothing to stop you except running into the spacecraft, which is what you want, so it'll work. Okay? Strange, but true. Okay? It is something that astronauts have to be worried about. It was something that science fiction did a terrible job of showing for years and years and years in space. Okay? But now, more modern science fiction shows are actually doing a very good job of showing, look, you don't move in space. Like the whole rescue scene for Mark Watney in The Martian. Okay? They were worried that they were going to miss him because they would have too much velocity. They were just going to go right past. They had no way to slow down until they blew up the door to the docking bay, okay, and let all the gas go out, and that created a slowing, a decelerating force, okay, that allowed them to slow down and capture him. And so it's realistic stuff. Okay, understand that inertia is related to the mass of an object. So your tendency to keep doing what you're already doing, which is what Newton's first law says you will do, is entirely related to your mass. I mean, think about this. If you've got a little kid riding towards you on a tricycle, okay, at like 5 meters per second, you just reach out and stop them, okay? Because they don't have very much inertia. They're small. A train doing the same thing, moving towards you, 5 meters per second. Now, 5 meters per second doesn't seem very fast, but it's fast enough. Okay, you are not going to reach out and go, you're not going to stop it. It's got too much inertia, okay? And you don't. okay, and you will be flat. Right? It just won't work. Your inertia is related to your mass. The more mass there is, the harder that object is to change its inertia. Okay? Just trying to get something moving. Okay? I mean, you got a ball on the floor, okay? You give it a little kick and off it goes. Okay? You have a big giant sphere made of lead. Is it as easy? It's still a ball, but man, it's got a lot more mass. Okay? Just giving a little tap isn't going to do anything. Okay? You have to like really push hard in order to get it moving because it has more inertia. What?
How do you define inertia?
Basically, you define inertia by an object's mass and its tendency to continue doing what it's doing. Okay? Either moving at a constant velocity or being stationary. Okay. Now, any change in inertia requires a force. If I want that desk to move, I got to go over there and make it happen. It's not going to happen on its own. I got to pick it up and move it. Okay? Now I've exerted a force on it. Okay? Now I can change its inertia. Okay? Before that, I had no chance of doing that. It wasn't just going to move. Okay? Regardless of how much I want to have Jedi skills. Okay? There was no way I was just going to make it move from over here. Right? Everybody follow? Okay. So what is a force? Okay? Force is going to be the most important word that we use in this unit. A force is very simply a push or a pull. Okay? If you push or pull something, you are exerting a force on that object. All right, so a tow truck pulling a stalled car, okay, pulls in this direction, right? The cable is angled, right? So it pulls, okay, somewhat vertically and somewhat horizontally. So is force a vector quantity? Definitely. Okay? Force is a vector quantity. It has magnitude and direction. Okay? If we're talking about a projectile, okay, what force is always acting on the projectile? Gravity. Okay? That's why it follows that arc. Okay? If you want to push over a wall with a bulldozer, you exert a force against the wall. Okay? The wall exerts a force back, but if yours is bigger, you move. It moves the other way. Okay? Incidentally, that's really important in terms of car crash safety. Okay. Head-on collision, smart car, semi-truck. Who wins? Semi-truck, every single time. Okay? Unless the smart car is moving at like relativistic speeds, then it might do some damage. But I mean, realistically, a smart car never wins that. Why? It's small. Semi-truck has got way more mass. Okay? Mass matters. Okay? It is the thing that determines your change in inertia. Okay? And in a car crash, okay, the winner of a car crash, make no mistake, if you've ever been in a car crash, there's a winner and a loser in every crash. Okay? The winner is the more massive vehicle. Always. Okay? Its velocity will change less. And it's your change in velocity that hurts. Okay? That's what causes damage, that's what causes injuries, okay, is that rapid change in velocity. The bigger, more massive object always experiences less change because of its mass. Okay? So what's the most important safety feature in your car? Mass. You either have it or you don't. Okay? Yes, wearing your seatbelt is important. I'm not saying just drive something really heavy. I mean, yeah, if I'm driving a tank, I don't need my seatbelt. There probably isn't even a seatbelt in a tank. Okay? First off, I'm way heavier than anything. I'm armored and I have a big gun. Okay? But I don't have a tank. So, okay, mass is the most important safety feature that your car can have. If you drive a small car, you don't have that safety feature. Okay? You have some, but not more than most vehicles. That's why we have seatbelts. Okay? Seatbelts are important because they keep you in the car. Okay? That is the most important function that they serve. You are far less likely to be injured by staying inside the vehicle, okay, than if you are ejected from the vehicle. Okay? So what seatbelts do is they keep Newton's first law from killing you. Because if you have a head-on collision, let's just say with something stationary, like a pole, okay, and you're not wearing your seatbelt, where do you go? Out the window. Why?
Because you're going to keep moving at the same velocity.
Exactly. Because of Newton's Newton's first law says that an object will continue to travel at a constant velocity until acted upon by an external unbalanced force. You're not wearing your seatbelt, that external unbalanced force is windshield, road, other bad things, okay? You don't want that. You want to stay in the car. The seatbelt saves you from Newton's first law. Okay? Second most important safety feature, airbags. Okay? Seatbelt keeps you in the car. Airbag slows you down gently. Anyone ever been hit by an airbag? It hurts. It's like a punch in the face. But it's way better than hitting the steering wheel. Okay? Back before airbags and collapsible steering wheels, anyone who was in a car accident had the same scar. Right here. Okay? Right across the scalp. Because that's where they go forward, okay, before like shoulder harnesses and stuff, like you just have the lap belt. Okay, you get in a crash, and you go forward, okay, you hit the steering wheel. The steering wheel was hard, didn't have a breakaway steering column, you just hit it and it would peel your scalp back.
Oh, geez.
Yeah, oh yeah. Okay, it was a very common injury, and get your scalp sewn back on. Okay? Yeah, not cool, right? That's why they built now steering wheels to do two things. The steering wheel itself will collapse under a heavy impact. Don't try it. Okay? Like you can physically collapse if you hit it hard enough. Okay? And the steering column, okay, the part that attaches, that actually steers your wheels, will also break away. Okay, so it'll retract away from you when it receives a certain amount of pressure. Okay? So those are safety features. Your airbag, what happens with your airbag is when you hit it, okay, the amount of time it takes your head to slow to a stop is much greater because it's like a big pillow, okay, than it is if you just hit the steering wheel. Okay? You just hit the steering wheel and your head just stops. Okay? That's concussion, that's peeled scalp, okay? It's all those bad things. Okay? Whereas if you hit the airbag, it's a much longer period of time. I mean much longer, I mean like a tenth of a second, but it makes a big difference, okay, in terms of the seriousness of any injuries you receive. Okay? So those are how your safety features work. Okay? One more safety feature. All cars are supposed to do this when they get in a crash. Crumple. Okay? Your car is designed to be destroyed in a crash. It is designed to sacrifice itself for you. Okay? It is designed to crumple up like a tin can. Because the more crumpling that happens, the longer the crash takes. The longer the crash takes, the less the acceleration you feel. Remember this formula? Okay? It's acceleration that hurts you. So, in a crash, you can't really control this number. It's probably 0, hopefully, and not something negative, meaning you're moving backwards after. Okay? But that you really can't control either. Maybe you hit the brakes, maybe you take a few meters per second off before the crash, but you really can't control VI. All the safety features in your car, the airbag, the seat belt, the crumple zones, are all designed to make T bigger. Because if T is bigger, what happens to A? It gets smaller. Okay? If I divide by a bigger number, A is smaller. Okay? The safety features in your car work on that formula. Okay? They work to make the acceleration smaller so that you are less injured. Mass also helps because of Newton's second law. The net force experienced by an object is mass times acceleration. Okay? So your acceleration is based on the force you experience divided by the mass. So the bigger the mass, the less the acceleration you experience. That's why mass matters. Okay? Those two formulas that all safety engineers work on. Okay? Anything they can do to make those work in your favor is what they will do. All right. So, mass. Mass is how much you what?
Mass is how much
Okay, that's what most people say because that's what in North American society we're always told. Mass and weight are the same thing. Mass and weight, mass and weight. No, they're not. Okay? Mass is how much of you there is. Okay? If I want to lose weight, all I have to do is go to the moon. I'll weigh 1/6 what I weigh here. That's massive weight loss. Okay? but there's still just as much of me there as there is here, okay? I'm no less massive, okay, on the moon than I am here, right? But that's the way we talk, okay? Oh, I gotta lose some weight. Oh, I gotta lose some weight, go to a higher altitude. You'll weigh a little bit less, okay? But there will still be just as much of you as there was before. Unless you walk there, then you might burn some calories and maybe drop a few, but, okay? Yeah, you gotta lose mass. Mass is how much of you there is. Weight is the force of gravity pulling on your mass, okay? We actually calculate that this way. The force of gravity is your mass times the acceleration due to gravity, 9.81 on Earth, okay? So if I lose mass, do I lose weight? Mass times gravity, right? If this number gets smaller, this number gets smaller too. So yeah, by losing mass, I do lose weight, okay? But I can lose weight without losing mass. I just have to change the acceleration due to gravity. Okay, if I can change that, I'll feel lighter. Okay? I won't be lighter, but I'll feel lighter. Okay? I mean, you think about it, you go to the International Space Station, you feel weightless, okay? But you still have mass. All right, so mass is the amount of matter that an object possesses and is, as a result, a scalar quantity. Okay? I don't say my mass is 75 kilograms down. It's not. 75 kilograms is just how much of me there is. Okay? Now my weight, on the other hand, okay, 700 and some newtons down. It's a force. It's a vector quantity. Gravity pulls me down. Okay? So it's a force. So force and, weight and mass are two different things. Okay, so weight and mass are two entirely different things. The weight we feel when we pick up a heavy object is the force of gravity acting on the object's mass. Okay, therefore, weight is the force of your mass. Okay. All right, questions on that? Okay, so according to Newton's first law, okay, if we use hockey as an example, if there's a puck on the ice, nobody does anything to it, the puck will stay right there. Okay, that's what Newton's first law says. An object at rest will remain at rest until acted upon by an external unbalanced force. Okay, if that puck is sliding and the ice is perfectly frictionless, the puck will not change velocity at all and would just continue to slide. Okay, in the same way that an object in space will continue to move through space and not slow down. Okay, unless it's acted upon by some other force. Because it's a perfect vacuum, okay, and there's nothing there to slow it down. All right, I'm going to show you an example of that. Got some decent movie physics and some like not so decent movie physics. Okay.